My name is Jared Coleman, and I will be presenting our work on message delivery in the plane by robots with different speeds. The problem we study is very simple to state. Given a set of robots in a plane with different speeds and a message which needs to be transmitted from one point on the plane to another, how can robots cooperate to bring the message from the source to the destination in as little time as possible? There are a few other rules to the problem. Robots can only acquire the message by picking it up at the source or by face-to-face encounter with another robot that already has it. We call this a handover. We assume robots can always travel at their maximum speeds and that direction changes and handovers are instantaneous. We're interested in finding both offline and online algorithms. In the offline case, robots know the starting positions and speeds of all other robots in advance. In the online case, however, robots know only their own speed. In both cases, the source and the destination of the message are known by all robots. Communicating mobile agents have been used to address many problems, such as search, exploration, broadcasting, converged casting, patrolling, connectivity maintenance, and area coverage. Data delivery and coverage cast with energy exchange under a centralized scheduler has been studied, and a restricted version with N mobile agents with limited energy on a line segment has been considered before. Additional research under various conditions and topological restrictions has also been studied. Our problem was also previously studied on graphs, and it has been shown that the problem with K agents on a graph with N nodes and M edges can be solved in big O of Kn log n plus Km time. We leverage this algorithm in the development of our approximation algorithm. Finally, our work is related to the Pony Express communication problem, for which optimal offline and online algorithms for the Anycast and broadcast variants on a line segment have been proposed. To our knowledge, the planar case has not been considered previously. Throughout the paper and this presentation, we use the competitive ratio to measure the quality of online algorithms. The competitive ratio is defined as the maximum over all instances of a problem of the online solution over an optimal offline algorithm solution for that instance. Our goal is to minimize this competitive ratio for online algorithms. In this presentation, I'll present the following results reported in the paper. First, an optimal offline algorithm for the two-robot case. Then an algorithm which approximates the optimal delivery time to a factor of square root of 2. Then, for two robots, we propose an online algorithm with a competitive ratio of 1 over 7 times 5 plus 4 times the square root of 2, and show that the same algorithm has a competitive ratio of at most 2 for n robots. Then we present lower bounds using different approaches. Finally, I'll wrap up with a conclusion and a discussion of possible future work in the area. We start with the optimal offline algorithm for two robots. So we consider two robots with distinct speeds. The slow robot travels with a speed of 1 and the fast robot with a speed v greater than 1. There's three cases we have to consider. First, if the fast robot can reach the source before the slow robot, then clearly it should just deliver the message by itself. Similarly, if the slow robot can deliver the message entirely by itself by going to the source and then the destination faster than the fast robot can even reach the destination, then it should also just deliver the message by itself. This case could occur if the fast robot is initially very far away from both the source and the destination. The interesting case is when the slow robot can reach the source faster, but it can't then reach D before the faster robot can. In this case, the optimal solution will involve a handover between the robots at some point M in the plane. Since the first two cases are trivial, the problem reduces to finding this point M in case 3. In order to do this, we make a few important observations about this mystery point. First, we prove that wherever this point is, it must take each of the two robots an equal amount of time to reach it by moving directly towards it. The idea for this proof is that if one robot could reach M before the other, then it might as well keep moving directly towards the robot it's waiting on to acquire the message sooner. Since the handover is always from the slow robot to the fast robot, this could only increase the average speed of the message and decrease the distance it must travel. When the slow robot's starting position is at the source S, this meeting point relates directly to an ancient theorem by the Greek philosopher Apollonius, which states that the trajectory traced by a point P which moves in such a way that its Euclidean distance from a given point S is a constant multiple of its Euclidean distance from another point K is a circle. In other words, the Apollonius circle between the robots, defined by lemma 2.2 here, is the set of all the points such that the robots can meet by moving in straight trajectories at their respective speeds. This is the set of all possible meeting points that satisfy the requirements given by the previous lemma 2.1. So for the two-robot case, where the slow robot starts at the source, the solution involves both robots moving toward a point M on this Apollonius circle to meet for a handover, so that the fast robot can then take the message and deliver it to D. Equipped with this property, we can write the algorithm and prove theorem 2.1, which claims its optimality in that it can be implemented to run using a constant number of operations. The first two lines of the algorithm handle case 2, where the slow robot should deliver the message entirely by itself. Note that case 1 is impossible in this scenario since the slow robot is assumed to start at the source. So the rest of the algorithm handles the third case. First, we observe that in some configurations, the fast robot should simply move directly toward the destination and the slow robot toward a point on its path to hand over. This occurs when the path from the fast robot's initial location and the destination intersects with the Apollonius circle, as you can see in this figure. That's the case that the control statement in line 4 handles. In all other cases, though, the fast robot must move toward a point M on the Apollonius circle and then change direction to move toward the destination. For this case, the key observation is that the points K, M, and D define an ellipse where K and D are its foci and M is a point on the perimeter. With this interpretation, the M which minimizes the sum of Km plus MD forms an ellipse which intersects with the Apollonius circle at exactly one point. In the paper, we provide a formulation of this problem which can be given as input to equation solving tools like Mathematica to find a closed form solution. To generalize this solution to cases where the slow robot does not start at the source, we follow a similar process of first characterizing the point M and then using equation solving tools to find a solution. For this case, the key observation is that while the slow robot goes to S and then to M, the fast robot should move directly towards M. In the figure here, Q is the location of the fast robot at the time the slow robot reaches S. Then, with some algebra and reparameterization, we prove lemma 2.5, which reframes the problem as an optimization problem. Finally, the general case algorithm for two robots is given. Lines 1 through 4 handles cases 1 and 2 from the beginning of the discussion, and line 6 can, again, be found using tools like Mathematica. We provide a link to a Mathematica implementation in the paper. While the equations derived in the previous section could be generalized to solve the problem optimally for any number of robots, we're not able to solve the resulting set of equations. Instead, we provide a square root to approximation algorithm. First, we consider a rectilinear solution to the problem, where robots can only move horizontally and vertically. In other words, rather than moving directly from B to P, a robot would need to move from B to Y and then from Y to P. Then we claim that any solution which is optimal subject to these rectilinear movements is a square root 2 approximation to the Euclidean solution, which is fairly easy to see. Then, using this idea, we provide the following algorithm and prove theorem 3.1, which states that the algorithm can find the optimal solution up to an arbitrarily small constant error. Essentially, the algorithm involves discretizing the space into a grid graph with delta over epsilon squared vertices and edges, and leveraging the previously mentioned results from Carvalho to find the optimal solution on the graph. This solution is an arbitrarily close approximation to the rectilinear solution, and therefore is a square root 2 approximation to the optimal Euclidean solution up to an arbitrarily small additive factor. Next, we provide an online algorithm and prove bounds for the 2 and n robot cases. The algorithm is very simple. Each robot simply tries to deliver the message entirely by itself, by going to the source and then to the destination. Consider the time t when the robots reach m in the optimal solution. Then t star, the optimal delivery time, is given by this equation. Then let x be the distance from the source to m, and a be the distance from the source to the destination. Observe the slow robot delivers the message in time t plus a minus x, and the fast robot delivers the message in less than time t plus a plus x over v. Then the competitive ratio C2 can be written, and the maximum is when the two arguments of the min expression are equal, which is when x equals a times v minus 1 over v plus 1. After some further simplification, we produce an upper bound which depends only on v and is maximized when v equals 1 plus the square root of 2. This gives us the desired upper bound. We also show this competitive ratio is tight by providing an example configuration where the value is a lower bound. In the example, the slow robot is initially placed with the source at 0, 0, the destination at 1, 0, and the fast robot at square root 2, 0. Now, we prove an upper bound of 2 for the same algorithm on multi-robot systems. Suppose the optimal solution delivers the message in time t star. Then, since our proposed algorithm involves no cooperation between agents, we must show that there exists at least one robot in the system that can deliver the message in time 2 times t star. In other words, we must show that in order for the optimal delivery time to be t star, there must exist a robot I starting at a distance si from the source with speed at least 1 plus si over 2t star. To prove this, we suppose by contradiction that no such robot exists, and show that the system cannot possibly deliver the message in time t star. We allow robots to choose everything else about their positions to minimize the delivery time, and show that even with an infinite number of robots placed along the lines so that they continuously hand over the message to the fastest robot possible, the delivery time must be greater than t star. We do this by observing that a message at position x at time t on the line segment must be being carried by a robot with speed less than this value here. This comes directly from the constraint on the robot's speed given its starting position. So the speed of the message must satisfy this inequality, which, given the initial condition that the message starts at the source, yields this constraint on the message's position with respect to time. This directly shows that delivery time must be greater than t star, a contradiction. To sum up, this proves that any configuration which can deliver the message optimally in time t star must include a robot that can deliver the message by itself in time 2 times t star. Next, we prove a theorem which shows that for any number of robots n, there is a configuration for which the proposed algorithm has competitive ratio 2 minus 2 over 2 to the n minus 1. Our goal is to construct an instance with meeting points given by mi here. We define the robot's initial positions, pi, and its speed, vi plus 1, specifically so that each robot executing the algorithm delivers the message to the destination at exactly the same time. Then, we set the fastest robot speed to 1, and the speeds and positions of the rest of the robots can be computed by their definitions. Since the fastest robot speed is 1, it starts at a distance 3 to the right of the destination, and so can deliver the message entirely by itself in time 4. Given its meeting point, the optimal delivery time is 2 plus 2 over 2 to the n minus 1, and so the theorem follows. Finally, we provide two lower bounds for systems with two robots. In the first lower bound, we assume that the speed of one of the robots is unknown, while in the second, we assume that the initial position of one of the robots is unknown. The second bound is slightly better, but we present both since they use different arguments, and it seems plausible that an improved lower bound may come from combining the two approaches. For the first lower bound, we consider a two-robot system, with one robot at the source and the other at a position k, with speed v greater than 1. The robot at the source's speed is chosen adversarially to be either 0 or 1. So the type of solution to the problem is clear. The fast robot at position k should move to some point x on the plane to meet with the slow robot. If the slow robot doesn't show up, the fast robot can conclude that its speed must be 0 and then complete the delivery by itself by moving toward the source and then to the destination. The competitive ratio can be obtained then by finding the equilibrium between competitive ratios given the speed of the robot, the slow robot, is either 0 or 1. In other words, the point we choose should be such that the adversary's choice makes no difference at all. We computed the best angles alpha, which defines the point M and the destination, and beta, which defines x, for the speeds v between 1 and 2, and found a maximum competitive ratio of 1.0391. For the lower bound, we consider the scenario with the source at the origin, the destination at this point D, a slow robot initially at the source with speed 1, and a faster robot either at K1 or K2. Drawn here are the two Apollonius circles and meeting points M1 and M2 of the optimal solutions if the position of the slow robot were known. The key idea here is that the point X that the fast robot should move to must be on the line segment SD, or else the adversary will choose the fast robot's initial position to be further away. Also, by a similar argument as was used in the first bound, the meeting point should be on the Apollonius circle. Using this, we computed the competitive ratio for different values of beta and obtained a maximum of 1.04059 with alpha equal to 0.8953 and the speed of the fast robot equal to 2.7169. In this study, we provided both online and offline algorithms for the message delivery in the plane by systems of mobile robots with different speeds and initial positions. We gave an optimal offline algorithm for 2 robots and a square root 2 approximation for n robots. Then we provided a simple online algorithm and proved tight bounds on its competitive ratio for the 2-robot and multi-robot case. Finally, we gave 2 distinct arguments for lower bounds on the competitive ratio of any online algorithm. There are many potential directions for further investigation. First, it isn't clear if there's an optimal algorithm for n robots. Also, in the online setting, there's still a gap between the lower and upper competitive ratio bounds. It would also be interesting to consider the problem where the message cannot be replicated. In our work, we rely on the assumption that robots can always acquire the message at the source. If the message is a physical object, though, and is taken away from the source by the first robot that visits it, the problem is slightly different. Finally, it would be interesting to consider the case where some robots in the system may fail. Thank you for watching. I hope you enjoyed the presentation.